Previously, we talked about Einstein's equivalence principle and pointed out how it was obviously wrong because the amount of force is entirely different on both sides. Since then, a debate board member by the name of Hubert had something to say about that. He said he disagrees with me, because in both cases, apple hits the earth and earth hits the apple, the forces acting on the apple and on earth, because of Newton's third law, are opposite and of the same amount. I think that is throwing all of the math out the window now, but before arguing about anything, let's talk about what Newton's third law of motion is. Newton's third law states, for every action, there is an equal and opposite reaction.
He knows a lot about the science stuff, Professor Dave explains.
As you sit in your chair right now, the force of gravity is pulling you down towards the center of the Earth. But something called the normal force points straight up with the same magnitude, which is why you remain perfectly still.
I'm sorry, Dave, but that chair is not pushing you upward. Though I know Professor Brian Cox claims the Earth is accelerating upward, I'm sorry to burst your bubble, but normal force does not exist.
What happens when you place an object on the table? The object exerts a force on the table, and the subject exerts an upward force on the object. There are two forces that result from this interaction: a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force.
This reaction force she is referring to is what people refer to as normal force.
What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one.
The problem here is that the table is not exerting any upward force on the ball. Forgive me as I exchange the soccer ball for a bowling ball here. But the forces in play in the table are horizontal, not vertical. The reason the ball does not fall through the table is because the strength of the table's molecular bonds is stronger than the weight of the bowling ball. If those bonds were weaker, like they are with water, the molecular bonds that hold the table together would break and the ball would fall right through. The same thing happens with your chair. If the molecular bonds that hold the chair together were weaker, you would fall right through. Your upward reaction force, or normal force, is simply an illusion. Now, pay attention to this 25-pound weight I have on the floor. Newton's third law states the floor is exerting 25 pounds of force upward onto this weight. Now I'm going to replace that weight with a 5-pound weight. If 25 pounds of upward force were being applied to that 5-pound weight, it should be rising upward. But Newton's third law says that for every action, there is an equal and opposite reaction. This means the upward force from the floor changes. It was applying 25 pounds of force, but now it is only applying 5 pounds of force. So in order for Newton's third law to be true, the floor has to pick and choose exactly how much upward force to apply with each object that rests upon it. That doesn't happen with molecular bonds. They are not picking and choosing. The molecular bonds are holding together with the exact same strength the whole time, and the moment that strength is overcome, the object falls through.
Think of a car hitting a brick wall. The car imparts an action force on the wall from its motion, and the wall imparts a reaction force right back on the car, bringing it to a quick stop. These vectors are equal in length and point in opposite directions.
Really, Dave? You claim that wall is pushing on the car with an equal amount of force? Though that car is pushing on the wall, that wall is not pushing back. The molecular bonds of that wall are just simply strong enough not to break. If they were weaker, the car would go right through the wall. If I were to have one car come and crash into an identical car traveling at the exact same speed in a head-on collision, that would be considered an equal amount of force. Herein, you should agree with me that that would be different than one car hitting a stationary wall.
This is illustrated by the following expression, where m1v1 plus m2v2 is equal to the sum of the masses times v final, which will depend on the magnitudes and directions of the two initial velocities. This approach can also be used to model car collisions, whether the two cars were moving in the same direction or opposite directions. Adding the masses of the cars and combining the velocity vectors will tell us what will happen after the collision.
Please tell me that you agree with me that the mass and velocity of a car plus the identical mass and velocity of another car is not going to be the same as the mass and velocity of a car plus the mass and velocity of a stationary wall. According to an auto accident attorney, head-on collisions are the most dangerous because the force of the impact is doubled due to the speed of each vehicle. Therefore, even a relatively slow auto accident with each car traveling just at 25 miles an hour will result in a tremendous impact equal to the force of hitting a wall at 50 miles an hour. This is literally as simple as 1 plus 1 equals 2 and 1 plus 0 equals 1.
The third law can sometimes be confusing, because it would seem to imply that no object could ever move, since any force accelerating an object must be paired with another in the opposite direction.
That is a really good point.
When hammering a nail into a piece of wood, the hammer imparts force onto the nail, and the nail imparts force onto the hammer.
No. If it was an equal and opposite force, the nail should not move at all.
But the nail is driven into the wood because there is a net force acting upon the nail from the motion of the hammer.
Since the nail does not exert an equal and opposite force, it moves. And since it is able to exert enough pressure on a given spot on that wood, it is able to break the molecular bonds within the wood and pass through it. If you disagree with me, please feel free to tell me why on our debate board. There's a link in this video's description. Just don't leave a shallow response like, "You are wrong," and just leave it at that. That is just saying, "I heard what you have to say, and I refuse to be persuaded by you." If you try to argue about it in the comments section, your comment will remain hidden. Our debate board was created to keep arguments organized in a systematic fashion, as science requires. Please feel free to check it out. This message was brought to you by the Flat Earth Institute of Science. Thank you for watching.